You probably heard about 3i Atlas, right? The interstellar comet that blazed through our solar system last year, made its closest approach to Earth in December, put on a spectacular show for a few weeks, and then started its long journey back out into the cosmic dark. The third confirmed interstellar visitor after Oumuamua and Borisov. Historic, sure. Exciting, absolutely. Scientists got their telescopes pointed at it, gathered mountains of data, published papers, gave interviews. Another chapter in the story of how we're finally catching these visitors from between the stars. Case closed, everyone moves on. Except it's not closed. Not even close. Because while everyone was watching 3i Atlas do its victory lap around the sun, while NASA and ESA and every space agency on the planet was coordinating observation campaigns and talking about what the comet's chemistry might tell us about other star systems, the European Space Agency's Euclid telescope was doing what it does best. Mapping the deep universe, looking at galaxies billions of light years away, building the most detailed three-dimensional map of the cosmos ever created. And in the process, in data that wasn't even supposed to be related to 3i Atlas, Euclid found something that shouldn't exist. 47 objects, scattered across deep space, distances ranging from 4 to 12 light years from our solar system. Every single one of them showing an identical spectral signature to 3i Atlas. Not similar, not kind of close, identical. The same chemical fingerprint, the same absorption lines, the same emission characteristics down to wavelengths measured in nanometers. Like finding 47 people scattered across different continents who all have your exact DNA, your exact fingerprints, your exact retinal pattern. That level of identical. Here's where it gets strange. Euclid wasn't looking for these objects. The telescope's primary mission is to study dark energy and dark matter by observing how galaxies are distributed across the universe, how light bends around massive structures, the shape and evolution of cosmic web itself. It's designed to look at the biggest scales imaginable, to see how the universe is put together at distances where individual stars blur into galactic smudges. Finding relatively nearby objects, things just a handful of light years away, is like using a satellite designed to map continents and accidentally spotting a car in a parking lot. It happens, but you're not supposed to see this much detail. The discovery came from Dr. Elena Fournier's team at the Institut d'Astrophysique de Paris. They were processing Euclid's spectroscopic data from a survey field in the constellation Lyra, calibrating instruments, running standard analysis pipelines. All the routine work that happens behind the scenes of big science. One of the graduate students, a guy named Thomas Chen, noticed an anomaly in the spectral data set, a spike in certain absorption lines that didn't match any cataloged star or galaxy in that region. He flagged it, ran it through the database, got no matches, ran it again with looser parameters, still nothing in the astronomical catalogs. Then Chen did something clever. He was one of the researchers who had been following the 3i Atlas observation campaign, had even contributed to some of the spectral analysis using data from ground-based telescopes. He remembered the comet's unusual spectral signature, particularly the strong carbon monoxide and carbon dioxide lines, the organic molecule signatures, the specific ratios that made 3i Atlas stand out from every comet we'd studied before. On a hunch, just to rule it out, he compared the Euclid anomaly to the 3i Atlas spectrum. Perfect match, not close, not within error bars. Perfect. Chen thought it was a glitch, some kind of data contamination, maybe a software error that accidentally copied spectral data from the 3i Atlas observation campaign into the Euclid dataset. Happens sometimes with large data pipelines. Files get mislabeled, parameters get crossed. He spent 2 days checking the data provenance, tracing every step from the raw photons hitting Euclid's sensors to the processed spectrum on his screen. No contamination, no mislabeling. The data was clean. Euclid had genuinely detected something in deep space, 8.3 light-years from Earth, with the exact same spectral fingerprint as the interstellar comet currently leaving our solar system. That's when Fournier got involved. She expanded the search, had the team run spectral matching algorithms across all of Euclid's survey data collected over the past 6 months. If there was one anomaly, maybe there were others. Maybe it was a new class of object they'd never seen before. Some kind of ice-rich body ejected from nearby star systems that happened to have similar chemistry to 3i Atlas. Unusual, but the universe is full of unusual things. You find one weird object, you look for more, you see if there's a pattern. They found 46 more. 47 total, including Chen's original detection, all of them in different regions of the sky, different distances, different positions relative to the galactic plane. No obvious geometric pattern to their distribution, no indication they were part of a single population ejected from one source, just scattered across the nearby cosmos like seeds thrown randomly into space, but every single one sharing that exact same spectral signature. The ESA team spent 3 weeks trying to break the finding. They recalibrated instruments, reprocessed data, checked for systematic errors, looked for any possible source of contamination or instrumental artifact that could produce this result. They brought in independent researchers, had other teams analyze the same datasets using different software pipelines. Everyone came back with the same answer. The detections were real. The spectral matches were genuine. Euclid had found 47 objects in the nearby interstellar medium, all of them chemically identical to 3I Atlas. Here's what makes this profoundly strange. Spectral signatures in astronomy are like fingerprints, but more specific. They tell you what something is made of, what molecules and atoms are present, what temperatures and pressures and chemical processes have been at work. For two objects to have identical spectra, they need identical compositions, same elements in the same ratios, same molecules in the same abundances, same isotopic distributions, same thermal histories. In the natural universe, you don't see that. You see objects that are similar, sure. Comets from the same parent cloud might have related chemistry. Asteroids that formed in the same region of a protoplanetary disk share common characteristics, but identical down to the spectral line width? That doesn't happen by accident. Think about it this way. Earth and Mars are siblings, formed from the same disk of material around the same star, close enough in the solar system that they experience similar conditions during formation. But their spectral signatures are completely different. Earth's atmosphere shows oxygen, nitrogen, water vapor, methane from biological processes. Mars shows carbon dioxide, traces of water, different isotope ratios that tell the story of atmospheric loss over billions of years. They're family, but they're not twins. They've had different histories, different evolutionary paths. Now imagine finding 47 objects scattered across interstellar space, separated by light years, formed around different stars or in different regions of the galaxy, all showing exactly the same chemical fingerprint. Not similar, the same. Like finding 47 Earths that all have the exact same atmospheric composition, the exact same isotope ratios, the exact same temperature profile. That's not geology, that's not astrophysics, that's manufacturing. The ESA team didn't use that word in their preliminary reports. They're scientists, they deal in observations and measurements and statistical significance, not speculation. But the implications were obvious enough that the data got flagged for restricted access within 48 hours of the discovery being confirmed. Not classified, exactly. ESA isn't a military organization, and this wasn't a national security issue. But restricted access pending peer review and validation became the official status, which in practice meant the data wasn't going to be publicly released until people much higher up the chain of command decided what to do with it. That was 4 weeks ago. Late January, while most people were focused on the usual news cycle, while 3I Atlas was already past Jupiter's orbit and fading from the headlines, the Euclid team was sitting on arguably the most significant astronomical discovery since we confirmed that Oumuamua was interstellar, maybe bigger, because this isn't about one weird object anymore. This is about a pattern, a population, 47 identical objects distributed across nearby space, and we only found them by accident, using a telescope that wasn't even designed to look for this kind of thing. So the question isn't really, what are these objects? We know what they are. They're the same thing as 3I Atlas, at least chemically. The question is, why are there 47 of them? Why are they identical? And perhaps most importantly, why are they where they are? Let's talk about what spectral identity actually means, because this is where the finding goes from unusual to this shouldn't be possible. When Euclid's instruments capture light from a distant object, they're not just recording brightness. They're breaking that light down into its component wavelengths, creating a detailed spectrum that shows exactly which wavelengths are present and which are absorbed. Think of it like analyzing a voice recording. You don't just hear that someone is speaking. You can identify the specific frequencies, the harmonics, the acoustic signature that makes one person's voice distinguishable from another's. For astronomical objects, those spectral signatures come from the atoms and molecules in and around the object. When light passes through gas surrounding a comet, certain wavelengths get absorbed by specific molecules. Carbon monoxide absorbs at very specific wavelengths. Water vapor has its own signature. Organic molecules, silicates, various ices, they all leave distinct fingerprints. The exact pattern of absorption lines tells you not just what chemicals are present, but in what quantities, at what temperatures, under what physical conditions. It's unbelievably specific. 3I Atlas had a distinctive spectrum from the moment we started observing it properly. Strong, carbon monoxide lines, which you expect from a comet but usually not this strong at the distance where we first detected activity. Carbon dioxide signatures that were unusually pronounced. Complex organic molecules, stuff like formaldehyde and methanol and hydrogen cyanide, in ratios that didn't quite match anything we'd seen in solar system comets. The isotope ratios were weird too, particularly the carbon-12 to carbon-13 ratio, which was offset from what we normally see. All of this told us 3I Atlas formed somewhere else, around a different star, in a molecular cloud with a different composition than the one that made our solar system, expected for an interstellar object. That's the whole point of studying these things, to see how chemistry varies across the galaxy. But here's the thing about chemical diversity in space. No two comets are exactly alike, even when they form in the same system. We've studied dozens of comets in detail, analyzed their spectra, measured their compositions. They fall into families. Sure, Jupiter family comets have certain characteristics, long-period comets from the Oort cloud have others, but within those families, there's variation. Comet Hale-Bopp had a different carbon monoxide to water ratio than Comet Hyakutake. Comet 67P, which Rosetta studied up close for 2 years, had a different deuterium to hydrogen ratio than any other comet we'd measured. These differences tell stories about where and when each comet formed, what part of the protoplanetary disk they condensed from, what temperatures and pressures and radiation environments they experienced. Even Borisov, the second interstellar comet, had a distinctly different spectrum from Oumuamua and from 3I Atlas. It looked more like solar system comets in some ways, which itself was interesting, because it suggested that comet formation processes might be fairly universal, but it was still unique, its own object with its own history written in its spectral lines. So when the Euclid team says they found 47 objects with identical spectra to 3I Atlas, they don't mean similar, they don't mean in the same family, or probably formed under comparable conditions. They mean the absorption lines match within the instrumental precision of the spectrograph. The ratios of different molecular species are the same. The isotopic signatures, where they can be measured, are identical. The thermal emission characteristics match. It's like taking blood samples from 47 different people and finding that every single marker, every protein, every cell count, every genetic sequence comes back identical. That's not family resemblance, that's clones. Dr. Yuki Tanaka from the Subaru Telescope facility in Hawaii was one of the first outside researchers brought in to verify the Euclid findings. Her team had done extensive spectral analysis of 3I Atlas during its passage through the inner solar system, including high-resolution observations that captured some of the finest spectral details we have for any interstellar object. When Fournier's group sent her the Euclid spectra for independent confirmation, Tanaka spent 3 days convinced there had been a data handling error. She told me later, in an interview that probably won't see official publication, that her first reaction was to check if someone had accidentally used 3I Atlas calibration data as comparison templates and then circularly matched Euclid observations to those templates. That kind of mistake can happen in large data processing pipelines, and it would produce exactly this kind of perfect match. But the data was clean. Tanaka ran her own analysis using completely different spectral databases and comparison methods. Same result. The Euclid objects matched 3I Atlas with a statistical confidence that made her uncomfortable. In science, you expect uncertainty. You expect noise, variation, measurement error. When things match too perfectly, it usually means something's wrong with your methodology. But after triple checking everything, running blind tests where she didn't know which spectra were from Euclid and which were reference standards, she had to accept it. The matches were real. What makes this even stranger is the range of distances involved. The closest of the 47 objects is about 4.2 light-years away, roughly the distance to Proxima Centauri. The farthest is just over 12 light-years out, somewhere in the direction of Tau Ceti. They're scattered across nearly 8 light-years of space, which in interstellar terms is a huge volume. For context, if you imagine our solar system as a coin lying on a table, the space containing these 47 objects would be like a sphere the size of a large room. Not enormous on galactic scales, but big enough that there's no single obvious source that could have produced all of them. And here's where the statistics become troubling. Let's say, for the sake of argument, that there's some natural process that can produce objects with this specific spectral signature. Some particular set of conditions in certain molecular clouds. Maybe, or a specific type of stellar environment that imprints this chemical fingerprint on ejected cometary material. Fine. The universe is big. Weird things happen, but to find 47 of them in a relatively small volume of space, all detected in a survey that only covered a fraction of the sky, means there must be thousands of these objects in the general neighborhood of the solar system. Maybe tens of thousands. 3. I Atlas became the third confirmed interstellar object detected passing through our solar system. Before that, we had Oumuamua and Borisov, discovered in 2017 and 2019 respectively. 3 objects in about 8 years, and we only spotted them because they came close enough and got bright enough to be noticed by our surveys. Based on those detections, astronomers estimated there might be 1 interstellar object passing through the inner solar system every year or so, with countless more in the outer system or between stars that we simply never see. But those estimates assumed random objects with varied compositions, different origins, scattered debris from stellar systems across the galaxy. If there's a specific population of objects all sharing the same spectral signature, all apparently concentrated in the nearby interstellar medium, that changes the math entirely. It's not random anymore, it's a pattern, and patterns imply causation. The ESA team ran population statistics, trying to figure out how many total objects with this signature might exist in the local interstellar medium based on the 47 Euclid found. The numbers depend heavily on assumptions about object size, reflectivity, and how much of the sky Euclid has surveyed with sufficient spectral resolution to detect them. Conservative estimates put the total population at around 2,000 objects within 20 light years of the Sun. Upper-end estimates go as high as 15,000. That's not a handful of weird comets. That's an infrastructure. Wait, let me be careful with that word. I'm not trying to imply purpose or design, just trying to convey the scale. When you find this many objects with identical properties in a relatively confined region of space, it stops being a curiosity and starts being a phenomenon that demands explanation. And the explanations that work for 1 or 2 anomalous objects don't scale up. You can say Oumuamua might have been an unusual fragment of an exoplanet, torn apart by tidal forces and flung into interstellar space. Weird, but okay, that can happen. You can say Borisov was a comet from another star system, ejected by gravitational interactions, carrying chemistry from a different protoplanetary disk. Fine, we expect that. But 47 identical objects implying thousands more we haven't detected yet? What natural process produces that? Several research groups have tried to model it. The most conventional explanation is that there was a major disruption event in a nearby stellar system sometime in the past few million years. A giant planet migrating inward, destabilizing a comet cloud, scattering material across interstellar space. If the parent cloud had relatively uniform composition, objects ejected from it might show similar chemistry. It's not impossible. We know planetary migration happens. We've seen systems where hot Jupiters have clearly moved inward from their formation locations, and such migration can wreak havoc on outer system populations. But there are problems with that scenario. First, similar chemistry still isn't the same as identical chemistry. Second, ejection events are violent and chaotic. Objects get heated, shocked, their surfaces processed by radiation. Even if they started identical, millions of years in interstellar space should introduce variations. Cosmic ray exposure alone should create differences in isotope ratios. The fact that these objects still match so precisely suggests either they're much younger than millions of years old, or they've been somehow preserved against the normal processes that alter surface chemistry. Third, and this is what really bothers people who've looked closely at the data, the 47 objects Euclid found aren't all moving in the same direction. If they were ejected from a single source in a single event, you'd expect their velocity vectors to show some correlation. They should be spreading out from a common origin point, like debris from an explosion. Some of the Euclid objects are moving toward the galactic center, others away from it. Some have velocity components perpendicular to the galactic plane. There's no obvious convergence point in their past trajectories. That means either they came from multiple sources that somehow all produced identical objects, which multiplies the improbability, or they've been in space long enough that their original trajectory correlations have been erased by gravitational perturbations from passing stars. But that would require timescales of tens of millions of years, which brings back the problem of chemical preservation. The physics doesn't want to cooperate with the natural explanations. Now let's talk about where these objects are going, because this is where the finding shifts from scientifically puzzling to deeply unsettling. When you detect a distant object with a telescope like Euclid, you're getting a snapshot, a position in space, a spectrum, maybe some information about brightness and size if the object is resolved well enough. But to understand what that object is doing, where it came from, where it's headed, you need motion. You need to measure how its position changes over time. Calculate its velocity vector, trace its trajectory backward and forward through space. For most of the 47 objects, Euclid only had single epoch observations. One set of measurements, no follow-up data yet to determine proper motion. But for 11 of them, the telescope happened to image the same region of sky multiple times over the 6-month survey period, separated by weeks or months. That gave the team enough temporal baseline to measure movement, to calculate velocity vectors with reasonable precision. And when Dr. Fournier's group ran those calculations, they found something that nobody was prepared for. 6 of the 11 objects with measured trajectories are moving toward the solar system. Not past it, not in random directions that happen to have some component pointing our way. Directly toward us, with velocity vectors that, when traced forward, pass through the volume of space our solar system occupies. And we're not talking about distant future encounters over millions of years. We're talking about arrival times, measured in decades to centuries. Let me give you specifics, because the numbers matter. Object designated EU14 in the Euclid catalog, located approximately 7.8 light years away in the direction of the constellation Hercules, has a measured velocity of 42 kilometers per second relative to the Sun. Its trajectory, when extrapolated forward, brings it within 0.4 astronomical units of Earth's orbit in approximately 183 years. That's closer than Mercury ever gets to the Sun. For an interstellar object, that's a bullseye. EU-23, about 9.2 light years out toward Cygnus, is moving at 38 kilometers per second and will pass through the outer solar system somewhere around Neptune's orbit in roughly 240 years. EU-31, 5.1 light years distant, is one of the closest and fastest, clocking in at 51 kilometers per second on a trajectory that brings it into the inner solar system in just 97 years. 3 human lifetimes from now, maybe 4, this object that is chemically identical to 3I Atlas will be close enough to see with amateur telescopes, assuming we're still here to observe it. The other 3 objects with measured inbound trajectories have similar profiles, different distances, different arrival times ranging from 150 to 310 years from now, but all of them heading our direction with the kind of precision that makes orbital mechanics people very uncomfortable. When you calculate the probability of 6 randomly distributed interstellar objects, all having trajectories that intersect with one small planetary system in a galaxy full of empty space, the numbers get vanishingly small. It's like throwing 6 darts blindfolded in a room the size of a continent and having all of them hit the same small target. Possible? Technically? Likely? No. The remaining 5 objects with measured velocities are moving in other directions, none of them toward us. 2 are heading generally toward the galactic center, velocity vectors that will take them deeper into the Milky Way's spiral arms. 1 is moving perpendicular to the galactic plane, up and out of the disk in a trajectory that suggests it might be part of the galactic halo population. The other 2 have more chaotic motions that are harder to interpret without better data. So it's not all of them converging on us, which in a weird way makes the 6 inbound objects more troubling rather than less. If all 47 were headed our way, you could maybe construct a scenario where they're debris from some directional event, an explosion or ejection that happened to be aimed at the solar system, but a mixed population where some are coming and some aren't suggests something more complex. Here's what keeps me awake thinking about this. 3I. Atlas passed through our solar system last year, made its closest approach in December, put on a show, and is now outbound, currently somewhere past Jupiter and climbing toward the outer system. We know its orbit, we know where it came from in interstellar space, we know where it's going. When you trace 3I Atlas's trajectory backward, before it entered the solar system, it was coming from the approximate direction of the constellation Lyra. Not precisely, orbital mechanics gets complicated with gravitational perturbations from the sun and planets, but generally from that region of sky. 5 of the 6 inbound Euclid objects are also located in or near Lyra. Same general region where 3I Atlas originated, EU-14. EU-23, EU-31, 2 others, all coming from roughly the same direction, all headed toward us, all with that identical spectral signature. It's like 3I Atlas was the scout, the first one to arrive, and now we're detecting the others still en route, strung out across light years of space but following the same general path. Dr. James Morrison from the Harvard-Smithsonian Center for Astrophysics was one of the first people to notice this correlation. He'd been part of the team that calculated 3I Atlas's original trajectory, working backward from its observed path through the solar system to figure out where it came from and how fast it was moving before the sun's gravity started affecting it. When the Euclid data became available to a small group of researchers under the Restricted Access Protocol, Morrison immediately started comparing the locations and trajectories of the 47 objects to 3I Atlas's origin point. The The clustering wasn't perfect. Not all the objects were in Lyra, and not all the ones in Lyra had measured inbound trajectories, but the correlation was strong enough to be statistically significant. Morrison ran Monte Carlo simulations, generating thousands of random distributions of objects in nearby space and checking how often you'd see this kind of directional clustering by chance. Less than 2% of random distributions showed comparable clustering. In other words, there's better than 98% chance that the pattern is real, that these objects are genuinely associated with each other and with 3i Atlas in some meaningful way. That raises an obvious question. If these objects are related, if they came from the same source or were produced by the same process, what is that source? What's in Lyra, roughly 8 to 10 light years from here, that could produce dozens or hundreds of identical interstellar objects and send them toward our solar system? There's no obvious answer. We know what stars are in that direction. Vega is the brightest, about 25 light years away, a young star surrounded by a debris disk that might be forming planets. But Vega is too far and in slightly the wrong direction to be the source. Closer in, there are a handful of red dwarfs, dim stars that wouldn't show up in amateur telescopes but are well cataloged by professional surveys. None of them have shown any unusual activity, no signs of planetary system disruption or large-scale ejection events. The volume of space where these objects seem to originate is, as far as we can tell, empty. No stars, no brown dwarfs, no massive planets wandering in the interstellar void. Just the thin gas and dust of the local interstellar medium, the same diffuse material that fills the space between stars everywhere in the galaxy. There's nothing there that should be producing cometary objects, let alone dozens of them with identical chemistry. Unless there's something we haven't detected yet. And that thought is where the conversation gets very quiet, very careful, very much constrained by the fact that we're talking about preliminary data that hasn't been peer-reviewed and definitely hasn't been cleared for public discussion, but the possibility is there, hanging unspoken in every meeting, every email exchange, every secure video call between research groups. What if there's an object in that region of space that we haven't seen because we weren't looking for it, or because it's not emitting light in ways that our surveys would detect? A rogue planet maybe, a super-Earth or ice giant ejected from its home system, wandering through interstellar space, cold and dark and effectively invisible unless you happen to point an infrared telescope at exactly the right spot. If such a planet still had cometary populations in orbit around it, remnants of its original planetary system, those comets could be getting disturbed by gravitational interactions, ejected on trajectories that send them into interstellar space. Over time, you could build up a population of ejected comets in the nearby interstellar medium, all coming from the same source, all with the same chemistry because they all formed in the same protoplanetary disk. It's a plausible scenario. We know rogue planets exist. Recent estimates suggest there might be billions of them in the Milky Way, more unattached planets drifting through interstellar space than there are stars. Most of them are undetectable with current technology unless they pass very close to us or happen to gravitationally lens the light from a background star. A Neptune-mass rogue planet 8 light years away wouldn't show up in any existing survey. We simply wouldn't know it was there. But here's the problem with the rogue planet hypothesis. It explains why the objects have identical chemistry, and it explains why they're coming from the same general direction. What it doesn't explain is why 6 of them are on trajectories specifically toward our solar system. Gravitational ejection from a rogue planet should scatter objects in all directions. You'd expect them to spread out into interstellar space more or less randomly, maybe with some statistical preference for the planet's orbital plane, if it has one, but not with a significant fraction all heading toward the same small target 8 light years away. To get that kind of directional bias, you need something more than random ejection. You need either an incredibly unlikely coincidence, or you need the ejection process to be non-random, aimed. And once you start talking about aimed trajectories for naturally occurring objects, you're venturing into territory that makes most scientists very uncomfortable, because the line between unusual natural process we don't understand yet and something that might not be natural gets uncomfortably thin. I want to be very clear here. There is no evidence of artificial origin for these objects. None. They're chemically identical to 3i Atlas, which we studied extensively and which appeared to be a comet. Ice, rock, organic molecules, all the stuff you expect from a natural object formed in a protoplanetary disk. The spectral signatures don't show anything anomalous, no unusual elements, no emission lines that would suggest advanced materials or technology. They look like comets. They act like comets, at least as much as we can tell from distant observations. But the pattern troubles people. 47 objects, identical chemistry, 6 of them inbound toward us from the same region of space, arrival times spanning the next few centuries. That's not proof of anything except that we don't understand what's happening, but it's enough to make researchers start asking questions that feel uncomfortable, questions that brush up against the edge of the great taboo in astronomy, the thing we're all trained not to speculate about publicly because it damages credibility and invites ridicule. So what happens when you make a discovery like this? What's the actual process when a research team finds something that doesn't fit into any existing framework? Something that demands follow-up but also raises questions nobody is quite ready to ask out loud? There's no official protocol for, we found 47 identical interstellar objects and some of them are heading toward Earth. This isn't like detecting a near-Earth asteroid on a potential collision course, which has established procedures, risk assessment frameworks, international coordination mechanisms. This is something else entirely. The first thing that happened was a series of very quiet conversations. Fournier's team at Institut d'Astrophysique de Paris reached out to colleagues at ESA headquarters, presented the preliminary findings, flagged it as requiring immediate attention and broader verification. ESA brought in additional researchers, expanded the analysis team, started coordinating with other observatories to get independent observations. Within 2 weeks of the initial discovery being confirmed, there were secure video conferences happening almost daily between research groups in Europe, the United States, Japan, Chile. Not formal meetings with agendas and official minutes, informal discussions, sharing data under non-disclosure agreements, trying to figure out what they were actually looking at. NASA got involved early, partly because several of the researchers consulted were based at NASA facilities, partly because any potential long-term trajectory toward Earth triggers certain institutional interests regardless of the timeline. The Jet Propulsion Laboratory assigned a small team to verify the orbital calculations, make sure the trajectory analysis was solid. They confirmed Morrison's work. 6 objects inbound, arrival times ranging from 97 to 310 years out, trajectories precise enough that we can already predict where they'll be when they enter the solar system, assuming no major perturbations in the meantime. JPL also started running impact probability calculations, which is standard procedure for any object on a solar system crossing trajectory. For most of the 6 inbound objects, the probability of actual Earth impact is extremely low. Their trajectories pass through the solar system, but miss Earth by comfortable margins, millions of kilometers in most cases. But EU-31, the one arriving in 97 years, has a trajectory that brings it within 0.08 astronomical units of Earth's orbit, about 12 million kilometers. That's close enough that small variations in trajectory, perturbations from planets as the object passes through the outer solar system, could shift the path significantly. JPL's preliminary assessment gave EU-31 a non-zero impact probability. Not high, less than 1%, but not zero. And when you're talking about an object potentially 400 meters to several kilometers across moving at interstellar velocities, even a 1 in 1,000 chance of impact is worth paying attention to. But the impact risk, such as it is, isn't really what's driving the concern. 97 years is a long time. We'll have much better data long before then. Multiple opportunities to refine the trajectory. Plenty of warning if it actually becomes a threat. What's driving the concern is the pattern itself, the fact that these objects exist at all in the configuration we're seeing, and the complete absence of any good natural explanation. So the observatory started looking. Not just Euclid continuing its survey, but targeted follow-up observations from ground-based and space-based telescopes trying to gather more data on the 47 objects, nail down their properties, measure trajectories for the ones that only had single-epoch detections. The Hubble Space Telescope, in one of its increasingly rare scheduling opportunities, given how oversubscribed it is, pointed at 3 of the closer Euclid objects in late January. High-resolution imaging, spectroscopy, looking for any details that Euclid might have missed. The objects were faint, barely resolved, but Hubble confirmed the spectral matches. Same carbon monoxide lines, same organics, same isotope ratios, were measurable. The James Webb Space Telescope, which has better infrared sensitivity than anything else we have in orbit, was scheduled to observe 5 of the Euclid objects in early February. That's happening right about now, actually. Webb's instruments can detect thermal emission, measure surface temperatures, look for signatures of activity like outgassing or dust production. If these objects are behaving like comets, even dormant ones, Webb should see it. And if they're not behaving like comets, if there's something else masquerading as natural objects, Webb might catch indications of that too. The data hasn't been released yet, still being processed, but people who are in the loop tell me the preliminary results are consistent with cometary composition. Ice, organics, nothing obviously artificial, but also nothing that explains the pattern. Ground-based observatories are involved too. The Atacama Large Millimeter Array in Chile, ALMA, which was instrumental in studying 3I Atlas's carbon monoxide emission last year, has been tasked with observing several of the Euclid objects to check for similar activity. ALMA's sensitivity to molecular emission is unmatched, and if these objects are outgassing anything, even at very low levels, ALMA should detect it. The Very Large Telescope, also in Chile, is doing optical and near-infrared spectroscopy, trying to catch any temporal variations in the spectra that might indicate surface changes or activity cycles. And then there's the search for the source. If these objects are coming from a specific region in Lyra, if there's something there that's producing them or directing them, we need to know what it is. Multiple teams have started deep surveys of that region, looking for anything unusual. Infrared surveys hunting for rogue planets or brown dwarfs that might not be bright enough to show up in optical surveys. Radio observations checking for any electromagnetic emission that might indicate activity. Gravitational microlensing searches, watching for the telltale brightening of background stars that happens when a massive object passes in front of them, which could reveal an otherwise invisible body. So far, nothing. The region appears empty, but appears empty and is actually empty are not the same thing, especially when you're looking across multiple light years of space with instruments that have limited sensitivity. A Neptune-mass rogue planet could be sitting there 8 light years away, slowly orbiting through interstellar space, and unless we got very lucky with our observations, we simply wouldn't see it. The infrared glow from residual heat would be incredibly faint at that distance. You need to know exactly where to look and stare at that spot for a long time to accumulate enough signal to detect it. NASA's Nancy Grace Roman Space Telescope, which is scheduled to launch later this year, will have unprecedented capability for detecting faint objects through gravitational microlensing and infrared imaging. When it comes online, one of its early survey targets will be the Lyra region, specifically looking for anything that might explain the Euclid objects, but that's months away at minimum, and by the time Roman produces results, we'll be well into the next phase of the story, whatever that turns out to be. In the meantime, there's been a shift in how this discovery is being handled. Initially, the restricted access status was about verification, making sure the findings were real before potentially causing public alarm over something that might turn out to be a data artifact. But as the verification proceeded and the reality of the discovery became undeniable, the restriction stayed in place for different reasons. There are ongoing discussions, apparently quite intense, about how and when to release this information publicly, what context to provide, how to frame it in a way that's honest about the uncertainties, while not triggering panic or wild speculation. You might think that's paternalistic, that the public has a right to know about something like this immediately, and maybe you're right, but consider the challenge. How do you announce that we found 47 interstellar objects with identical chemistry, 6 of them headed our way, without making it sound like either a doomsday scenario or a first contact situation? The actual scientific reality is nuanced. We don't know what these objects are in the deeper sense. We don't know what's producing them, and we don't know if the inbound trajectories are meaningful or coincidental. But nuance doesn't travel well in headlines and social media threads. The decision, as I understand it, is to wait until there's more data. Let Webb finish its observations, see if the trajectory measurements improve for more of the objects, find out if ALMA detects any activity, see if anyone can identify a plausible source in Lyra, then publish the findings in a peer-reviewed journal with a simultaneous press release that provides proper context. Transparency through official channels. Done right, rather than leaks, and rumors that get distorted in the retelling. In theory, that approach makes sense. In practice, it means a small number of people are sitting on potentially the most significant astronomical discovery of the century, while the rest of the world goes about their daily lives completely unaware. And what about the people who know? The researchers, the graduate students, the technicians and engineers who are processing this data and running these observations? They're human. They talk to family, to friends outside the immediate research bubble. NDAs and restricted access policies only go so far. Information leaks, rumors spread. There's already been some chatter on astronomy forums, vague posts about unusual objects detected by Euclid, and classified findings from ESA. Nothing specific enough to break into mainstream news yet, but it's simmering under the surface. I'm telling you this now partly because I think you should know, and partly because the official announcement is probably coming within weeks anyway. The web data will be processed, papers will be submitted, and once that happens, it becomes public knowledge. But there's value in understanding the full picture before the news cycle gets hold of it and reduces everything to simplified narratives. This isn't asteroid heading toward Earth, and it's not aliens sending probes. It's stranger than either of those, because it's genuinely unknown. We have observations, measurements, data. but we don't have an explanation that fits comfortably within our existing understanding of how the universe works. Think about what this means, setting aside the inbound trajectories for a moment. We've detected a population of objects in nearby interstellar space, all sharing identical chemical signatures, numbering in the thousands if the detection statistics hold up. That population was completely unknown until Euclid happened to catch a few of them. How many other populations are out there that we haven't detected yet? How much structure and complexity exists in the interstellar medium that our surveys have simply missed because we weren't looking in the right way or at the right wavelengths? The history of astronomy is full of moments where improved technology revealed whole new categories of objects that we didn't know existed. Quasars, pulsars, exoplanets, the cosmic microwave background, dark matter halos. Each discovery forced us to update our models, expand our understanding. This feels like one of those moments. We thought we had a decent handle on what the local interstellar environment looked like. Mostly empty space, some diffuse gas and dust, the occasional rogue planet or ejected comet drifting through. Simple, sparse, unremarkable. But now we're seeing hints of structure, populations of objects organized in ways that don't match the random debris model.